So let's, okay, we are going to start discussing the general issue, general construction of the Feynman path integral formulation. But before that, let us go from this abstract Hilbert space formulation to the ordinary language of wave mechanics. And so this is a slight detour. I would like to remind you what wave mechanics is. I say remind you because this is really the usual routine that people present at the undergraduate level. They start with a wave function, an attribute to the physical meaning, and then write the so-called wave equation of Schrodinger, and then you go on, build everything on it. Well, till now we have seen that the states in the abstract formulation are represented by a ket, which is a vector of a Hilbert space. If it is a continuous system, the Hilbert vector space, and that space then is a Hilbert space because it's infinite dimensional. We usually reserve the name Hilbert for the infinite dimensional case, but sometimes it is so, we are so used to using it. We use the name Hilbert space for all vector spaces in quantum mechanics. So it's a misnomer, but still let's go on with that. And we have constructed out of this a time evolution equation. Remember, using the basic principles of time evolution, etc. And this turned out to be the Hamiltonian, such that these states, well, first of all, these states, in order to attribute them a physical meaning, they should be normalized. And you'll see what that normalization means in the present context when we move into the wave mechanics. And we have also constructed, well, it was really quite the opposite. So therefore, let me put this arrow as a two-sided arrow. We have constructed this time evolution operator, e to the minus I over h bar. Well, of course, it's not as simple as that. So in the most general case, we constructed it as an infinite series. Yeah, let's start from the right. So, well, in principle, the solution to this formal integration or solution to this equation is this in general. Well, there are, of course, special cases when h is time independent, then you can integrate this. H time independent, then this expression becomes well, of course, let's interpret this. You start at a time t0, you prepare a state, you know everything about this, and then you would like to predict the value of the psi at a future time t, and this is the operator, and when you take this operator and act on the initial state, psi t0, and this ut t0, that gives you the future state in a causal, unique manner. That's interesting. Remember when I started in the first hour, I talked about the causality and determinism in detail because there are usually some misunderstanding and misinterpretations about this. This equation is causal. The solution is presented as such in detail. Once you specify the initial value of the wave function, you can predict the future value of the wave state vector exactly. That's the causality. Determinism is something else. It is, of course, the physical meaning that you attribute to these state vectors themselves. We have a probabilistic determinism. We discussed that in detail in the past. I don't want to lose that much time. I started with the time evolution problem because you'll see that post-integral formulation is really exclusively constructed on the time evolution business. Time evolution operator sandwich between the state vectors of the position operator, to be precise. So we have to really know what it is. This is the specific case. That's the general solution of that equation. Well, there you could have other specific cases. The Hamiltonian may be time dependent, but different values of Hamiltonian at different times may be commuting. And we have seen examples of it for the spin precession case in an external magnetic field. We will pick it up later when we go to that point. So let's proceed to save the time as much as possible. So this is what the abstract Hilbert space description of the quantum mechanics. So we would like to go from here to the wave mechanics. Well, wave mechanics is constructed on the following property, that you have this state vector, which is an abstract ket, satisfying certain set of mathematical properties. And of course, you can expand this in any basis you like. What is the basis? Complete set of orthonormal unit vectors in the Hilbert space. Complete set of orthonormal unit vectors. How do we choose them? Well, first of all, we are doing physics. It's not an abstract mathematics. We have the observables. Observables are those Hermitian operators living in the Hilbert space. That is position and the momentum and the Hamiltonian and any other thing like angular momentum and stuff like that you can think of. Therefore, these are Hermitian, and we have at the beginning we have demonstrated a very simple but very important theorem that eigenvectors of Hermitian operators corresponding to different eigenvalues are orthogonal. Well, of course, the first leg of the theorem was simpler. The eigenvalues are real. Hermiticity guarantees that they are real, and the eigenvectors corresponding to different eigenvalues are orthogonal. You normalize them to make them physical. Well, as I said, we have discussed that normalization and physical meaning of the normalization in the past, and we'll pick it up again in the new context. Well, this is the old context. It is new context for us in this class, because we haven't started with the wave mechanics. We have started from the abstract formulations, and we are reaching these points bit by bit, slowly, okay? So what are the possible bases that you can think of expanding this? Well, the things which comes to your mind are those which we have employed and worked on it in the past. And also you may think of having energy eigen. Well, let me use this funny notation, energy eigenvectors. Well, that is, the eigenvectors associated with the Hamiltonian operator directly. And anything else you can think of. Think of any observable, this Hermitian operator, and their complete and orthonormal eigenvector basis. And this is an arbitrary vector, and you can expand it in terms of that. And the claim, the basic postulate of quantum theory, the information contained in this arbitrary state is contained in the right-hand side in the expansion. You may say, is this really the basic postulate? Yes, this is the basic postulate, and that's miraculous. It is not a trivial thing. Some of you may think it's trivial. No, not at all. That whatever is contained in the general state is contained in the expansion in terms of any observable eigenvectors. Okay, so let's start with the most popular one, which we have been using till now. What we do, the trick also, I think you have by now get used to the idea, then this is the completeness relation, right? Identity, you insert that identity here. And if you are using the second basis, you insert the completeness of that observable's eigenvectors, or vice, etc. So that's a very nice, quick way of constructing the expansion. So what do I have then? The QX and the vectors, the basis vectors. And I will remind you what that normalization is. How do I express normalization? And this quantity, this coordinate in the spaces, the sum and the basis vectors EI and the VI, if it is. Okay, it's too pedantic. I apologize for giving such a pedantic analogy. It's a three-dimensional vector, right, in here. The vector represented by an arrow, and there is the summation over each individual coordinates along the three basis unit vectors. That's that expression, really. Once you really get used to this coordinate language, this language, everything becomes so beautifully simple. Huh? So you can use your experience, not all the time, but however, some of the experience you got used to in the 3 dimensions. So this is the state vector. And that's the wave function that I was talking about. Well, there are certain things that we have to settle quickly in relation with the old description, right? That's the old quantum theory, sort of, in terms of the wave mechanics. That is, in terms of these wave functions. Well, there are two things that we have to settle. The equation of motion in terms of this. Second, the physical interpretation of the psi. Okay, let's pick them up one by one, and let's bring up the old information that you are more familiar probably in this context. So let's address the issue of equation of motion. Okay, here is, well, the equation I have already written down. I have started with, so here is the psi of t, d cube x, nx, and psi xt. So what do I have to do in order to be able to use the previous equation? I have to act on it by this. So what do I get if I act by that? D by dt, psi of t, d cube x, x. Now it enters this. X doesn't depend on the time explicitly. We are in the Schrodinger picture. Therefore, eigenvectors do not depend on time explicitly. There is only one place in that expansion which contains time dependence, is psi of xt. So time derivative acts on it. I insist on the difference between, subtlety in the notation, although sometimes I know that it doesn't catch the attention of the students as much. In the left-hand side is a straight, it is here the partial. Why? Because this thing is a function of x1, x2, x3, and t. So t is one of the 4 variables, really. In the left-hand side, that abstract vector depends on the single variable t. Therefore, it is straight derivative in the left, it's partial derivative in the right. So that is what I have in the left-hand side of that equation I have erased. What about the h? Now I have to act on it. Next, I have to act on it by the h. H on psi of t, d cube x, h on x, psi of xt. This is an eigenvector of the position operator. That's Hamiltonian operator. Notice that it acts on it. What is it? H is p squared. Well, that is an operator we carry from the classical physics. The Hamiltonian for velocity non-independent potentials. It is the p squared operator divided by 2m plus the v of x. These are operators. Remember my notational convention, I use capital letters to represent the operators and the small letters for the eigenvalues and eigenvectors. When there is a danger of confusion, when there is no risk, we proceed with the ordinary alphabet, right, x and p's. Here there is a need for distinguishing the operators from the eigenvalues. Therefore, I use this capital notation. So this is the momentum operator. That's the potential. Potential is the function of a position operator. I look at that particular class of physical problems. Well, there are more general classes, right? Like the electromagnetism, which contains velocity-dependent potentials. Generalization to that is trivial, but for this, setting the stage and establishing the notation, it is sufficient to work through with that simple example. Nice. Once we have reminded ourselves what the H is, what we have to do is to remember the action of the position operator and the momentum operator on the eigenvectors of the position operator. Well, that's the definition of the position operator eigenvalue equation, so that's simple. But what about the P? P acting on X is what? IH bar d by d gradient X. Okay. I have talked about the sign subtlety before, therefore I skip, and you'll see how it comes back again. When a momentum is acting on functions of X, it acts like h bar over I, that is minus IH bar d by dx. When it's acting on the position operator eigenvectors, because of its very definition of being the generator of the translations, it is this sign. Pay attention to it. Remember, work on it a little bit on your own. In the past, I used to ask this question frequently in the exams because I want to see what you are talking about. What is the meaning of the things that you are writing down? Huh? It's not simple, stupid mathematics. There's physics in it. Anyway, so what do I do then? Well, you may say, does it matter in this problem? No, it doesn't. Well, what I'm trying to say that you have to write the correct things. Why it doesn't matter? Because if I take the p squared to get the Hamiltonian, when it's acting on here, of course, taking the square of plus IH bar or minus IH bar does not make any difference. Of course, we are aware of it, but still, we insist in writing the correct things. So what is this thing then? d cube x minus h bar squared over 2m del squared, well, of course that's with respect to the x, plus v of x now. Why? Because if capital X is this, then any function of capital X is f of x on x is f of x, x. Using that theorem, so this becomes v of x number, c number x, acting on x times psi of xt. So that's the right-hand side of the equation. Continuation is there. That's the left-hand side of the equation. In order to be able to compare those and take advantage of the linear independence of the x family, being complete and orthonormal, this x eigenvector basis is linearly independent. In order to take advantage of it, I have to somehow move this from here to here. How do I do that? Well, it's easy. That's a c number function of c number x. These are derivatives, square. I have to take integration by parts twice. Taking integration by part twice, when you are not that careful, you may think it's safe if you adjust the mathematical properties of the functions under control such that you can drop the integration by parts. Well, when it's infinite space, it's more or less trivial. When it's finite space, you have to, of course, bring in the boundary terms, term contributions coming from the surfaces. But anyway, be careful about this. Why the contribution coming from the surface at the infinity, including the entire space? Well, because it is a normalization of psi guarantees the dropping of those surface terms. I will re-elaborate it quickly, but anyway. So you integrate by parts twice, move this block from here to there. And so what do you get? d cube x minus h bar squared over 2m d squared x plus v of x psi of xt. That's in the desired form. That's the right-hand side, and that is the left-hand side. And these x's are linearly independent. Therefore, if we collect everything to the left, we collect everything to the left and write it in the form IH bar d psi dt, and better notation is this, minus h bar squared over 2m del squared plus v of x psi is equal to 0. X's are linearly independent, therefore the solution to this equation unique solution, right? Linear independence is guaranteeing it. Perhaps you're more familiar with the discrete version of this. You have a Fi is equal to 0. The only way that these CIEI for the three-dimensional case is 0. The only way this equation is satisfies is that, right? So using that, then I get the equation. That's very nice, very satisfying, right? You feel more comfortable now because we have obtained the Schrodinger's equation, wave equation, which has really set the stage for the quantum theory. This is considered to be the starting point of the quantum mechanics in early 1926. With that equation. So we have the equation. Now you say we know it. Of course we know it. But the emphasis is different, mathematical emphasis. So what is the physical meaning of psi then? Well, psi is, in order to understand the physical meaning of psi, we have to reconsider the normalization. Remember at the beginning when we were listing the properties of the state vector psi of t, we said that it must be normalized. And this was so important. In a sense, all the physical transformations we were considering, like the space translation or time translation, time evolution that is, we have insisted that the state remains, it keeps its norm. They are norm-preserving transformations. So it led to the fact that those physical transformations, that time translation or space translation, are unitary transformations to preserve this norm. Well, when you look at it in this form, you say, it's not something I'm familiar with. Wait, now we'll demonstrate what that means in terms of these wave functions. So what is how do I expand this in terms of the coordinates, the wave functions? Then you expand this, d cube x psi of xt, and that's the ket. And this one in the bra, you go to the dual space, remember, we have worked on those details. So what do we have? D cube y psi star of y and t. And that's the corresponding expansion. When you are in the ket space and go to the bra space, you can complex conjugate the numbers, Hermitian conjugate the operators, bras correspond to the kets, etc. There's a set of rules, right? Etc. So what is this thing then? This thing is d cube x, d cube y, psi star of yt. I don't think it's a good idea to continue in here. I will write it in here. D cube x, d cube y, psi star of yt, psi of xt, and yx, right? That's how I hit the psi bra with the psi ket. Well, they are orthonormal, and they are also normality, which we have discussed in detail in the past, so let's not elaborate on it that further. It's a Dirac delta normalization. These are continuous spectrum operator observables. You carry out one of the integrations taking advantage of this, then that gives you d cube x psi of x t t squared. You say, of course, now I feel more comfortable. This is the thing that I have known from the beginning. Let's put those things together here. Let's clean up a little bit here. We have demonstrated that in this expansion, in terms of the spaces, these coordinates, and the psi, these coordinate functions satisfy the following property. And what is the physical meaning of this? Well, the physical meaning of this is buried in itself. Psi x psi of t. The probability density, because it's a projection, right? It's the coefficient. Probability density of finding the object represented by psi at the point x at time t. Nice. Then those densities squared and added up, you get the probabilities. Density is mod squared, you get the probabilities. The sum over all options is 1. You throw a dice, you get one face. One of the 6 faces with the probability 1 over 6. What is the probability of getting any one of those faces? It is the sum of all the options, 1 over 6 plus 1 over 6 plus 1 over 6. All 6 times is 1, 100%. So it's very satisfactory that we now close the circle and we go back to the conventional wave mechanics from the abstract Hilbert space formulation of quantum theory, and the coordinates in the x spaces are the wave function, all wave functions. Now, let's talk about the stationary state. Pick it up again, the concept of stationary state. We have seen that, well, the detail is, okay, perhaps let me remind you. The detail is the following. If A is an operator observable such that it commutes with H, then these two operators have common set of eigenfunctions. Then what you do, you go to the eigenvalue equation of the A. Again, the capital letter, small letter, is the usual description of eigenvalues. Let's take it to be AI. Let's have a discrete spectrum. I don't like the book's notation. He uses too many primes, and it's really cumbersome. If we have a discrete one, of course, the other notation has the advantage that it can be used for the continuous spectrum as well. But the argument doesn't lose any from generality. So when you have such a thing, then what is the physical outcome which comes out of these two statements? They should have common set of eigenvectors, and this is the eigenvector equation, eigenvalue equation for the A. Then we say A and psi, A and H will have common set of eigenvectors. Then, how do we proceed? We proceed in the following manner. If A is how do I represent? What is the time evolution of these AI vectors? How do they evolve? Well, they evolve under the time evolution, a general time evolution rule, right? If H is itself time independent, then this is e to the minus I over H bar HT, starting at t equals 0 or t. Let's take the T0 is equal to 0 to make notation simple. AI, right? This is how, as any arbitrary state evolves for time-independent h like that, then it evolves like this too. Now h AI are also common states. AI are common eigenvectors of the H as well. But let's write that statement. What is AI? Well, this is EI-AI. You have two commuting operators, H and capital A, and they will have common set of eigenvectors. Of course, with different eigenvalues. Eigenvectors are the same, but that is the eigenvalues of H in here. Therefore, this evolution becomes AIT e to the minus I over H bar EIT AI. Now, what is the associated wave function? Instead of talking about an arbitrary wave function, I am talking about the wave function associated with the eigenvector of the A. Perhaps some of you have felt which way I am moving, right? So x e to the minus I over H bar EIT AI, and this is e to the minus I over H bar EIT x and AI. This is a general theorem. As general as possible, we have seen this. So some of you may say, do we need such a most general form? Of course not. But if we start with using the A directly as H itself, without enlarging the system, you may think that it's so narrow. It's not. So what if I choose the A to be H directly? Then this problem is telling you that the time-evolved energy eigenfunction is a phase times the energy eigenfunction at t equals 0, right? That's the thing. Well, these are the states which are called stationary states in general, although they have an explicit time dependence in this fashion. When you compute the expectation values in these states, you get that those expectation values are time independent, as we have demonstrated. Okay, that's the reason of terminology. Stationary state, meaning expectation values are time independent. Good. So if we take these kind of stationary states, what do you get if you get those stationary states? IH bar dy dt x ai of t minus h bar squared over 2m del squared v of x x ait. Now you write what x ait e to the minus I over h bar eit. And this one is e to the minus I over h bar eit times x and ai, times x and I. And that's the only place where there is time dependence, and it brings down what ei over ih bar, which cancels. So you get the following. E x ai is equal to minus h bar squared over 2m del squared plus v of x, x and I. If AI is the energy eigenfunction, this is more general than this case, special case. If it is the energy eigenfunction directly, this is psi e of x, right? Take AI to be the h itself. And this is, and you again feel comfortable. Oh, this equation I know. This is the time-independent Schrodinger equation. These terminologies are sort of futile now, childish, because we have more general, rigorous formalism to get them. Anyway, the old language in the, you say, freshman physics level, you have a time-independent differential wave equation, the usual Schrodinger, and you have a time-independent Schrodinger equation like that. And these psi e x's are the energy eigenfunctions. Because this is the Hamiltonian operator in the x spaces. It's acting on that wave function, giving back the same wave function time and number. This is typical eigenvalue equation. And then naturally, then this time-independent Schrodinger equation is nothing but the energy eigenfunction. All terminology, really usual and routine. Before really turning our attention to more rigorous, more challenging issues, perhaps you may wish to recall, again I say recall because you have seen those things in a different context. Well, once you have an equation of this form, either the full form time dependent or the special form time independent, well, that's the second degree differential equation, right? Partial. And you have the partial differential equation theory techniques under control, so you can really address any physical problem you like, provided that V is given. If V is specified explicitly, and the famous ones are the Coulomb one, right? Coulomb problem of the hydrogen, minus E squared divided by R, or isotropic oscillator 1/2 m omega squared R squared, or simple harmonic oscillator, one-dimensional 1/2 m omega squared X squared. They're well known, and when you substitute those explicit forms of the potentials, ensuring that boundary conditions are satisfied. In all these three problems I have stated, the relevant boundary conditions are satisfied for the existence of non-singular solutions in the physical region. Then you can solve for the wave function explicitly. In the previous hour, remember, we have constructed these solutions of the simple harmonic oscillator using operator techniques. We introduced a set of operators, A and A dagger, although they are individually non-Hermitian, and we have had a beautiful formula, a very algebraic operator. Again, we have been able to construct the explicit solutions of the simple harmonic oscillator. It's not the Well, there are not that many problems that you can handle so successfully using that algebraic method, but thanks God the simple harmonic oscillator is so simple indeed, we could solve it. The alternative method is to solve this problem for the simple harmonic oscillator case, one-dimensional for instance, then you write V of x equals 1/2 m omega squared x squared, and you have seen how to do it in the undergraduate courses. And you get a Gaussian, beautiful Gaussian suppression factor times the Hermite polynomials. And the degree of the polynomials are dictated by the physical condition, right? N. If you are looking at the second or first or the 27th energy eigenvalue, that dictates what would be the degree of the Hermite polynomial, right? Hermite polynomial's degree is an important issue. Well, anyway, I think that's good enough. So we close the circle commenting on the stationary states and how to handle them. Before jumping into our next beautiful challenging subject, let's elaborate a little bit on the interpretation on the wave function. Those of you who are a little philosophically oriented might have already seen some works still being published in philosophy journals and so on and so forth. What is the physical meaning of wave function? Why it is complex? So why is so and so? So it's really important things. We are not doing mathematics, we are doing physics. So the physical interpretation of wave function is really important. For example, is wave function a physical thing? Probably you have never thought of it. X, position, momentum, energy, angular momentum. But the wave function, we know how to use it. But is it really physical? Is it something which is measured and observed? If you go to certain journals like Physical Review Letters and look at some of the recent issues, you'll see that there are discussions of that sort and new papers coming out on the physical nature of the wave function itself, ontic or epistemic descriptions, and wave function versus measurement. For example, what is the gap in the Hilbert space between different physical wave functions? Beautiful subjects. You see that I'm one of those who enjoyed those things and working sometimes on it. But anyway, so it is not an obscure or exotic question to say, what is the physical meaning of wave function? And underneath there are as all those questions that you can ask yourself, enjoy yourself. Physical meaning. Well, I have already mentioned that the psi of xt is the coordinate in the x, that is position operator eigenvector basis, and it has the physical interpretation, the following physical interpretation. It is the probability density. This is the probability density. The thing without, this is the amplitude, probability amplitude. And this is the probability density of finding the object at time t at point x in a unit volume near that, around that x. And it is normalized. Obviously, this is to make it non-negative. That's an important property of probability theory. You construct a probability theory by listing the axioms. Probabilities are non-negative numbers, and they add up to 1. Non-negativity mod squared, and add up to 1. Some challenging again question on your free time. Why not psi to the 4? Or why not the real part of psi or imaginary part of the psi, but to make it real? To make it real and positive. So psi mod squared. What if you construct an exotic scheme by taking psi to the 4, mod 4? Anyway, I don't know. This is the minimalistic and a very effective version that you construct your theory on. And also, I have reviewed, not discussed, when I was making the initiation to this class. And we can repeat the argument, but there is no need for this. And you see, this equation is satisfied as a byproduct of the equation of motion itself. We have said that this satisfies a certain equation of motion, but these are physical things, really. That's probability amplitude, that's the probability density, non-negative, and add up to 1, satisfying 2 postulates of the probability theory, and it satisfies this continuity equation. You may say, so what? Well, you'll see what that so what means. Continuity equation. The terminology is historical. I think it looks like the fluid equation, therefore rho is the density. Perhaps I have to stick that rho in here as I use this new notation. Well, the rho, what I mean by rho is this. So if we work out the J, what do we get? I assign this as a private homework. I'm sure you have done it in many times in the past. So it's not that big a problem. It shouldn't take more than a few minutes that you can construct. What that J is then? J is h bar over 2mi psi star del psi minus the psi del psi star. So you prove the equation and you get that as a byproduct. So what is it really? Let me rewrite it slightly differently. Let me use the eraser, and I invite you to please rewrite the equation once more. If I move that 2i underneath, a complex expression minus its conjugate divided by 2i is what? It is the imaginary part, right? So J is this. Obviously, you have to notice that we have used, in deriving this, we have used, although it is intrinsically trivial, V Hermitian. to have Hermitian Hamiltonian, to have all those nice postulates, all those mathematical properties. But I'm emphasizing this here that we use the fact that for this equation we use Hermitian to open a new window to a more general discussion. What if there are non-Hermitian V's in the game? What is the continuity equation then? Discuss it on your own. Make a note of it, please. What if there exist non-Hermitian V's? Physically, it means leakages out or leakages in. A non-Hermitian piece is a source of decoherence. So the equation really is to be modified, and there is a right-hand side which tells you that not all the probabilities that you are losing from one region moves to another one, and some of them decoheres. It goes out, leaks out. So hermeticity is a guarantee for the conservation of probability. If it is non-Hermitian, it's not conserved. By the way, that's the expression for the J. What is the immediate consequence of this equation? To close the circle back to what I have listed already, if you integrate this over all space, d cube x, d rho xt, dt is minus d cube x, dj. Well, that's the famous Gauss Theorem. The volume integral of a divergence can always be converted to a surface integral. That surface is the boundary, right, of the volume. If it is the entire space, it is the surface at the infinity, ds j. That surface grows like r squared. It's the spherical surface in 3 dimensions. It's a two-sphere. Then it grows like r squared. If the density, current density, decreases faster than 1 over r squared, it's safe. Does it decrease faster than 1 over r squared? Let's try to have a feeling. It is this expression, really. Psi. And there's a derivative of psi. It's not psi squared, really. It is suppressed further, because when you take the derivative, you decrease the degree of r by 1. The ideal coordinates are those spherical polar coordinates, because 2 of the coordinates are compact. 1 of them is non-compact. So r and theta phi. Theta phi is compact. R is the one which may move from 0 to infinity, which changes. If it goes like 1 over r to the alpha. Derivative goes like 1 over r to the alpha plus 1. So it's 1 over r squared, r to the power 2 plus alpha. If alpha is non-negative, then indeed this grows faster. It goes to 0 faster than 1 over r squared, and so the surface integral is 0. Why it should go faster than 1 over r? The square integrability of psi itself, the existence of probability, psi mod squared being finite, guarantees that it goes faster than 1 over r. So you see how it is closed. The existence of this thing, in order to be 1, it should be finite, then guarantees that psi goes to 0 faster than 1 over r, actually 1 over r to the 3/2, to be precise, and that guarantees the killing of that term, and it enables you to move this derivative out straight again. You may get tired of my insistence of this straight and partial difference, but trust me, that's so important. d by dt, d cubed psi mod squared is 0. So you will normalize it at the beginning, it stays normalized ever. Again, time evolution. I'm walking around the time evolution, and after the break, we'll jump into the path integral formulation. Okay, that's, I think, it for the time.